In this video, I'll show you how to predict what the current will be in certain branches of a circuit if you know the current in other branches. And this is the beginning of circuit analysis, the ability to tell what current and voltage and resistance will be in a circuit without actually building the circuit. So here's an example to start with on the left, and from the example, we'll build up to a law. So here in this light, you measure that the current going through it is 5 amps. There's a fork here, and in this light, you measure the current as 2 amps. And so you're asked to predict what will the current be in that light and in this light down here. If you want to pause the video, go ahead and do it, and then I'll write in the answers. Okay, so 5 amps through this one splits into 2, and this will be 3, which you probably predicted and got right. Then the two branches reunite here, and all 5 amps go through this one. So the answer to that is 5 amps. If you had any trouble with that, a good analogy is to think of it like cars. 5 amps means 5 coulombs per second. 5 of something, like 5 units of charge per second going through this light. So think of it as like cars per day. Instead of coulombs per second, think of it as cars per day. All right? And this 5 means you can imagine 5 cars, there's 5 cars, go down that road in one day, and then there's a fork, and this tells you that 2 of the cars go through this road. So this question here is asking you how many cars have to go down this road, and of course the 5 splits into a 2 and a 3. Then a little later in the day, we ask you how many cars go down that road. Well, of course, they reunite, and you get all 5 cars on that road there. And that explains the numbers over here. It's like how many cars in one day. That's what these numbers are telling you. Okay, let's go on to the law for this. This is called Kirchhoff's law. He has 2 major laws for circuits. This is his first one, and it's for electric current. Kirchhoff lived in the 1800s, and he worked with circuits, of course. Here's the law. At any point, this is true for any point in any circuit. You put your finger on that point, and you say, okay, at that point, add up all the current going into that point, and it will always equal what? Pause the video and write down or think about what would go in that box. The total current going into a point has to always equal the total current coming out of that point. So the total current out. If you want to get used to the symbols you'll have to use in higher level math and physics courses, this means total or summation, that's current in. And so pause and think what you would write there. Maybe write it down on a piece of paper, and it would be this. Okay, here's 2 examples. Currents represented by red arrows, and we have numbers by them. Here's the point, and the point is represented by a black dot. Here, into this point, you have 9 amps of current. And then coming out 2, 1, and 6 amps on these 3 branches. So the total going in is 9, the total coming out is 9. If you want to think about this for a minute, what it actually means is the charges, the electrons, can never kind of bunch up and spend time there. Whatever goes in 1 second has to come out in 1 second. They also likewise can't spread apart. They can't disappear, and you can't get more suddenly appear. So the number of electrons that go into a point in 1 second has to equal the number coming out. This is kind of obvious to a lot of people because there's those branches, but it's also true even if there's 1 line in and 1 line out. So here's a point in a circuit. If you say there's 9 amps going in, then there must be, if you want to pause it and write what goes in the blank, okay, there must be 9 amps coming out. That's what this law says. All right, and finally we'll end the video with some examples that will prepare you to do future homework problems. Okay, if you just want to look at this and try pausing the video and filling them all in, or you may want to pause after I do each one, but what I'm going to do is fill them in assuming that you can pause at any time. Okay, 7 amps here, this must be 7 amps. Notice current does not get smaller as the charges flow through the circuit. That'd be like thinking the number of cars starts getting smaller on the highway. As you go down the highway, the cars start disappearing. This is charges per second like cars per day going through that light. So if 7 cars go through that light in one day, where do they go? They must go through the next light. All 7 have to go through that light in the same day. All right, down here we have 20 amps going through this, splits into a 6 and 14 amps. All right, and then finally on this big one, Notice what's given up here, IB. That B stands for battery. That means the current through the battery is 8 amps. And then try filling all the blanks. Pause it if you have to, and I'm going to fill them in. There's no forks here, so all 8 coulombs that go down here in 1 second have to go through this. So you have 8 amps of current. Notice how the lights are labeled, I1, 2, 3, 4, 5, and the battery current is labeled with a B. Sometimes it's labeled with a 0 in my handouts. All right, this 8 amps of current splits into a 3 and a 5. And then this 5 has nowhere else to go, so that's also 5. And then down here at this fork, the 5 amp current coming from this direction reunites with the 3 amp coming from that direction, and this might be 8. This has to be 8 amps. And then finally, you could ask for what the current is through a section of the wire. And this would also be 8 amps because there are no forks. All 8 coulombs that go through this light in 1 second continue and go down this wire in 1 second.